Welcome to the thesis defense of Masoud, and a special welcome to our external expert, Professor Thomas. Thanks for coming, for supporting us, and we do appreciate it. Thanks a lot. Thank you, Hans, for coming. Thanks a lot, and to everybody. And now Peter will be a very short introduction, and then we start.
Okay. Thank you very much, Silvio, for this introduction. And also welcome from my side. I would like also to start here with thanking Michael Kalmer from Basel University for his role as external reviewer and examinator here today during this PhD defense. So to our candidates, Masoud is originally from the Iran, and he studied chemistry at the University of Hamadan. And for his master studies, he went to Tehran University. And since 2012, he's a PhD student, originally in the group of Thomas Wandlowski here at the Department of Chemistry and Biochemistry. In 2012, he started his PhD project on molecular electronics. And today, we are going to hear a talk about charge transport study of functional molecules employing break junction technique under potential control. So I look very much forward to your exciting and excited presentation. The stage is yours.
Thank you very much, Peter, for the nice introduction. Good afternoon, everybody, and welcome to my PhD defense. As Peter said, I'm going to talk about the charge transport studies of single molecules under potential control. So, to start with, I've divided my presentation in four different parts that you can see here. First of all, I will start with a small introduction, answering the question what molecular electronics is and why do we need molecular electronics. Then I will start with the experimental part about the instrumentation, data analysis, and the definition of electrochemical gating in single molecular conductance measurements. Then I will go on with the project that I have done during my PhD using different molecular systems from redox inactive to redox active and the molecule with high on-off ratio. And I will end up with the conclusions, summary, and the outlook of this study. So let's start with the definition what molecular electronics is. So by definition, molecular electronics is the relatively new field in science which is dealing with the investigation of the charge transport or thermal transport properties of single molecules or the assembly of the molecules. Why do we need to measure these charge transport properties of these molecules? The idea is that we can apply this single or assembly of the molecules as building block of the electronic instrument, like you can see here, a resistor. It can be wire, switch, transistor, or all the other electronic compartments. So what the question now is that why do we need this single or assembly of the molecules for applying in these electrochemical electronic circuits? So here you can see the map provided by Intel in 2015. It's seen easily that the silicon technology that we are using nowadays is moving toward the miniaturization. So according to the MOSO, the number of the transistors that we are applying in a certain circuit is doubling like every 18 to 24 months. But the problem arises when we reach to the size below 7 nanometers. So at this size, the quantum effects are interfering and this macroscopic physical law fail. So we need to find an alternative option toward this silicon technology that we are using nowadays. One of the best alternatives could be single molecules as building block of this electronic instrument, because these single molecules have several orders of magnitude smaller size than the equivalent silicon-based compartment, and also they have a higher energy gap that we don't have this leakage of the electron between these compartments sitting next to each other. So now we know about the necessity of the molecular electronics, but we need some instrumental setup, some techniques to measure the conductance of these assembly or single molecules to be applied in these electrochemical electronic circuits. So there are several techniques have been developed during the last years. Some of these techniques are dealing with the assembly of the molecules. Many of them are sitting on the surface we sandwich them between two electrodes, and the average of the conductance is measured in this configuration that we can see here. Two examples of them are current sensing atomic force microscopy, and another example is mercury draft. Another kind of techniques that have been developed for this purpose are dealing with the single molecular conductance measurements. This one single molecule is attached between two electrodes with some techniques, and the conductance of this single molecule is measured in the junction. So one of the most sophisticated and robust and reversible techniques that have been developed for this measurement is based on break junction technique. So by definition, break junction involves an instrument, an electronic instrument, with two metal leads and a very thin gap in between, and the molecules during the stretching process can be trapped between these two metal leads, and the conductance or charge transport properties can be measured when they are in the gap in this junction. Three of them that we are using in Bern I've shown here. It's conductive probe atomic force microscopy break junction, mechanically controllable break junction, and scanning tunneling microscopy break junction techniques that we are using in our lab. So the working principle of these three techniques are more or less similar. They are based on break junction. I will talk about STM break junction technique, but what I'm going to explain can be applied in two other techniques as well. So for the STM break junction technique, we can see here we have a tip which is positioned on top of the substrate. The substrate is already modified by the molecules of interest. We have the feedback control of the tip above the substrate. So we switch off this feedback and tip moves toward the substrate until it reaches the preset upper limits of the current. So this preset upper limit of the current usually corresponds with the formation of several metal-metal junctions. So we can see it here, this metal-metal junction. After a few milliseconds, relaxing of the tip into the substrate, we start withdrawing the tip from the substrate, and we break this metal-metal junction with a certain rate which is withdrawing. So until we reach to this point that we can see we have monoatomic gold-gold junction. It corresponds to one gold atom or metal atom in the tip and one metal atom in the substrate. This is called monoatomic junction quantum conductance. So with breaking this metal-metal junction, we form a very thin gap at the sub-nanometer level, and the molecules are surrounding the tip and substrate. They can be trapped. When this gap forms, and with further pulling away, we can break this metal molecule metal junction, and this is the end of the cycle for a break junction technique that we can see here. So how do we acquire our data for this measurement? Usually with applying a bias potential between the tip and the substrate that we can see here, we form a diagram that we call it conductance, distance, traces here. It has several features, and I try to explain very briefly about it. So the zero here is showing this monoatomic metal-metal junction. We call it quantum conductance, and it's equal to 77.5 microsiemens by volume. So after breaking this metal-metal junction, we have a very sharp decrease in the conductance value, which is like around more than 3 orders of magnitude. We call this region jump out of contact region, and we have two scenarios after this jump out of contact. If we don't have any molecule, if we have just a blank experiment, or molecules they don't have like proper anchoring group or the proper structure, we don't see any peak here. It just goes directly to the noise level of our instrument. But if we have the proper molecules that you can see here with the proper anchoring group, you can see a plateau related to the trapping of this molecule between two metal leads during the break junction experiment, and before we can see this plateau which is characteristic of the molecular junction, molecular conductance value. So here I've shown several examples of this measurement, different cycles. You can see with different colors, and clear plateau here for the molecule trapping between the two metal electrodes in this region. So later on, I will talk mostly about just STM break junction. I've used this method mostly for my PhD work, and it has several advantages over the other two techniques that I explained already. We have a better or more precise distance control or measurements. We can image the surface and focus the tip on the parts that we have the molecule, so we can measure the conductance at the substrate at the place that we have the molecules on the surface, or if you want to monitor the contamination in the surface, we can see easily. So STM break junction is not kind of blind experiment like MC-BJ. So the most important one is that we can easily apply electrochemistry for STM break junction. This is the main focus of this talk today, which is related to the electrochemical gating concept. So usually judging the conductance or charge transport of single molecule based on one single current distance traces or conductance distance trace is not logical enough, because we have the break junction system, very dynamic. Molecule slides between two metallics, and it forms many configurations when it's sliding, and each configuration has its own conductance value. So also we are measuring at room temperature. We have this thermal fluctuation in the energy level. So usually this plateau that you can see here is in the range, not in the exact value. What we do for this measurement, we do a statistical analysis. We form this two-dimensional histogram that you can see here, constructed from several hundred to several thousand of single current distance traces. There are several features that you can see in this two-dimensional histogram. Here it shows 0, the plateau is very small plateau for the monoatomic junction, a high density cloud of data for the molecular junction or the charge transport of molecule in the junction, and we can see the noise level of the setup here. So we form one-dimensional histogram that we can see the features more clearly. We have a very sharp peak here that you can see. It's for the monoatomic gold-gold junction or quantum conductance here. We have the molecular features at this region that we find the most probable conductance for this measurement, usually based on Gaussian fitting, and we have the noise level of all setup at this potential, at this conductance usually. Another data that we get with this break junction experiment is plateau length analysis for the junction. So there are many data also hidden in this plateau length analysis, but one of the most obvious ones that we can see, usually we see two peaks, one of them for the pure tunneling at around 0.5 nanometer, and the peak for the molecular junction. So easily from this data, we can estimate the junction formation probability for these measurements. So, but there are many other factors also affecting the conductance of single molecule in the junction. So obviously, if we change the structure of the molecule, we change the mechanism of the electron transfer, and we change the energy levels in the molecule. Therefore, we can change these transport properties of the molecule in the junction. Another factor is coming through the environmental control. If we have aqueous electrolyte, ionic liquid, polar solvent like organic one or non-organic one, so we can trigger many ideas, and we can control the conductance with controlling the media around the junction. Electrode materials can define the string of the molecular junction microbond to the electrode materials, and it can range from metallic one like gold that I have used in my work, platinum, aluminum, non-metallic like graphite or graphite. Anchoring group also can define the mechanism of the electron transfer, if it's hole or electron transfer in the molecule junction, or it can also define the strength of the bond. One of the most important factors is based on external stimuli that we have, like magnetic field that can control the spin of the electron in the junction. It can be, for the case of photo-switch molecules with light, we can excite the molecule or change the structure of the molecule, and therefore control or modulate the conductance. One of the most important one is electronic field control that is based on this electrochemical gating definition that I want to talk about now. But before talking about the definition of electrochemical gating in single molecular conductance measurement, I would like to talk about the word gating by itself, from where it's coming. This word actually is coming from the field effect transistors configuration, that we have source electrode, we have a drain electrode, and we have a gate electrode in this configuration here. We have a nanobias or a junction here, like a channel that we modulate the resistance between the source and between the drain electrode with changing the potential of our gate electrode in the field effect transistors configuration. This idea has been already applied to many molecular systems that you can see here. One example, we have here the source and drain electrode and the gate electrode here, 2 planes of graphene and molecule. The molecule, certain one, is breaching between these 2 planes of the graphene. So with this idea, it was proven already that we can control the Fermi level, we can shift up or down the Fermi levels of all electrodes, we changing the gate potential, we can change the redox state of the molecule in the junction here, we changing these 2 with this gate potential, or if we have the assembly of the molecules, we can change the assembly of these molecules based on gating control. But electrochemical gating in single molecular conductance measurement means simply measuring the conductance of single molecules under potential control. So for this purpose, we have an electrochemical cell here. We have control electrode, reference electrode, that we have 2 working electrodes that you can see here. They are substrate and tip. So we control the potential of the tip, substrate, and bias potential independently using a bipotential stat that we have here. And what's the difference between that gating in field effect transistor and electrochemical gating in the single molecular conductance measurement is coming through the fact that here our gate electrode is the reference electrode, which ideally has a constant potential by time. What we change here in this configuration, we change the relative potential of the tip and substrate versus the reference electrode. But as I said, in the gating in field effect transistor configuration, we change ideally the potential of our gate electrode to modulate the conductance. So electrochemical gating in single molecular conductance measurement means measuring this conductance under potential control. So what kind of opportunities can be taken using this electrochemical gating in single molecular conductance measurement? Here we can see the Fermi levels of the electrode, here molecular orbitals level, and we know that the charge transport in an open circuit experiment depends on the alignment of the molecular frontier orbital with the Fermi levels of the electron. So electron tunnels or hop from one side to another side, from one electrode to another one, and the conductance value can be measured in the open circuit experiment without any potential control. But if we have electrochemical gating control in our system, we can change the alignment of the frontier molecular orbital with the Fermi level of the electron, by shifting up or down these Fermi levels by controlling the potential in our setup. Therefore, we can modulate the conductance through the electrodes here. So we can control the conductance in a range that we change the potential for this setup. So here it shows a picture of our experimental setup that we have used molecular imaging setup, frontier front screws for manually adjusting distance of the tip and substrate. We have the setting motor for the rough adjustment, and we have a modified scanner for this kind of measurement. So here it shows a photo picture of the base plate that we are using with the substrate here, which is gold in most of the cases. We have platinum wire as reference electrode and control electrode. This platinum wire is quasi-reference electrode, but later in a real electrochemical cell, we calibrate the data versus a real reference electrode for this measurement. The tip is inserted into the scanner, and here is the base plate that we have, and tip is on top of the substrate for this measurement. And here it shows our argon chamber. We need to have environmental control for these measurements because the potentials that we are working are usually very negative potential, and this potential we have oxygen reduced in our setup, so we need to get rid of this oxygen in the measurement. So usually, based on the media that we have, we purge the setup for at least half an hour before the experiment, but if we are using ionic liquids that they are more viscous, we need even to extend the time to 1 or 2 hours. So with this introduction and the definition of electrochemical gating, now I talk about the work that I have done using this idea in different molecular systems. First, I start with a redox inactive molecular system For this purpose, we have chosen 4,4 pyridine that you can see the structure here. This molecule has several advantages over the other type of molecules. First benefit of this molecule is that we have a very narrow homolomo gap for this 4,4 pyridine. So if we shift up or down the Fermi level of the electrode, we can modulate the conductance more significantly compared to the pyrolanthane group, which is used mostly. Another advantage is coming through the fact that for the technical point of view, that we don't get any contamination from pyrolanthane group if we are using 4,4 pyridine. So we try to address several issues for this measurement. First, potential control or electrochemical gating and energy alignment. Of course, the molecular interactions in the interface of this project. So first, to begin with, we fix the potential at a certain value and we measure the conductance of 4,4 pyridine under potential control. We have seen three different things in the single current distance traces that you can see here and in one-dimensional histogram that are named by low, medium, and high conductance values. From the literature, we know that the low conductance value is coming from the configuration that the molecule is perpendicular between the two metal leads for this measurement. So when we have the molecule tilted between the two metal leads, we have the pi system or setup interacting with the electrode materials, and we add like additional channel to this measurement. Therefore, we have higher conductance for the medium state compared to the lower state conductance of 4,4 pyridine. But for the first time for this measurement, we have seen double junction that we don't see in the open circuit experiment. What's the reason for that? According to experimental evidences and on DFT calculation, of course the literature, we have found that this conductance for the high value is coming from the double junction when we have this interface properties control of the molecule on the surface of gold 1.1. So why it's because of double junction, the conductance of this state of the molecule is more or less twice the conductance of the medium state. And of course, based on Plateau length analysis, we have found the same plateau for medium and high conductance. It shows that the molecule is sliding. Or DFT calculation as well is showing the double junction for these measurements. So as the next step, we try to change the potential, to change the electrochemical gating potential for this measurement and monitor the conductance in the whole potential window available for this molecule in the aqueous electrolyte. So what we have seen was interesting with moving the sample potential with sweeping it to more positive value. We can see this gradual decrease in the conductance for these three different peaks. As I said already, in the benefits of electrochemical gating control, we have the frontier molecular orbital and the Fermi levels of the electrode. So the conductance depends highly on the alignment of this frontier molecular orbital with the Fermi levels of the electrode. So in the very negative potential, we have a partial resonance between two states, but when we are shifting the potential to more positive values, we are pushing the Fermi levels of the electrode far away from the frontier molecular orbital and from the off-resonance state, from the partial resonance state. In this region, we have off-resonance state at very positive potential. So that's why we can see this decrease in conductance. From the CD, we can see three different regions for this molecule interface properties on the surface. Here is the closed package structure, and here is rhombohedral structure. When we have the closed package structure, we have twice the density of the molecules on the surface. So here it's like half, and that's why we don't see the high conductance value for this measurement. And it's another experimental proof that we have double junction for that measurement. From the calculation point of view, our collaborators have calculated these transmission curves that you can see with the solid lines, and this shows for experimental result, which is in very good qualitative agreement with the theory. So now we know about the electrochemical gating and shifting the Fermi levels. In another collaboration with Professor Zhang in Chinese Academy of Science, we have synthesized and studied this molecule naphthalene diimide, which is a redox active molecular system. So it has three different redox states. It's shown here with neutral state, radical anion state and dianion state of these molecules. These three redox states are very stable in the ionic liquid that we have used, and here it shows the cyclic voltammogram for this measurement. With repeating this cyclic voltammogram, you can see a very big decrease in the intensity of the peaks, which shows that our molecular system in this ionic liquid is very stable. So why we are using this ionic liquid? It's also because these potentials are very negative potentials. So if we are using a coarse electrolyte, we have hydrogen evolution at this region, so practically it's not possible. As the next step, I try to monitor the conductance for these three different redox states of the molecules. And I divided this cyclic voltammogram in three different parts that you can see here with three different colors. The black color is showing the neutral state of the molecule. When we shift the potential, we sweep it to the more negative value here. Blue color corresponds to the radical anion state of the molecule, and the red is for the dianion state of the molecule. Single current distance series of the neutral state of the molecule is showing the field plateau at around 10 to minus 4. But when we sweep the potential to more negative value, that we have the radical anion state of the molecule, we can see a peak which is placed at in the conductance with 7 times more value than the neutral state. And when we shift more the potential to the values that we have the dianion state of the molecule, we can see 3 times more conductance value for this dianion state. So in the whole range from the neutral state to dianion state, we have the switching factor of more than 1 order of magnitude for this measurement. Here it shows the one-dimensional histogram of these measurements constructed from more than 1,000 single conductance distance traces, and shows a clear plateau at 10 to minus 4 and 2 peaks more for the radical anion and dianion state of the molecule with this shift that I have explained. The evolution of the conductance plateaus and the conductance can be seen here in 2-dimensional histogram with a clear data density at around 10 to minus 4, and inset is showing the plateau length analysis for this measurement with 2 different peaks that I have explained about the nature. So from this data we can see the junction formation probability around 80% for the neutral state of the molecule. So but when we are talking about the molecular switch, we have to check the reversibility of this switch, how reproducible this molecular switch is. So for this purpose, we have started with the neutral state of the molecule that we can see here, the peak. So we shift the potential to radical anion dianion state, and we sweep the potential back and monitor the conductance. We can see after 7,000 single current distance traces, still we can recover the peak for the neutral state of the molecule, which shows that our redox switch is very stable and reversible redox system. From the calculation point of view, for the first time with our collaborator, Professor Lambert in Durham, we have tried to simulate the double layer around the junction. We have introduced several charges here, you can see, with different distance from the plane of the molecule. We're playing with the configuration of these molecules around the molecular junction, and of course the distance. We have introduced 0 charge on the molecule for the neutral state, 1 charge for the radical anion state, and 2 charge for the dianion state of the molecule. Later, we have calculated the transmission curves for these 3 different states of the molecule with a double layer around the junction, and we have seen here a perfect qualitative agreement and trend with the experimental results. So up to now we know and we learn how to tune the Fermi level of the electron, shifting up or down in the case of 4-4' bifield in molecular system, and tune the conductance in the potential window available for this measurement. We have learned as well in the case of naphthalene imide molecule how to change the redox state of the molecule and switch the conductance between different redox state of naphthalene imide. So now we want to know if we can combine these 2 different ideas in one molecular system and see the both effects in just one molecule. We know that for a redox active molecule, we have the potential range which molecule is redox inactive, and we have a potential value that the molecule is redox active at this potential. So for this purpose, in collaboration with Professor Martin Bryce in Durham, we have studied these two anthraquinone-based molecular systems, which are named here with AQ15 and AQ14. These two molecular systems are different based on the electron pathways that they have. In the case of AQ15, the electron pathway is going through the anthraquinone moiety of the molecule. So, in changing this redox pathway, we can change the conductance theoretically. So, in the case of AQ14, the electron pathway is going through the benzene ring. This anthraquinone moiety is just like a side function of group for this measurement. The assembly of these molecules on the surface of gold bond one electrode is showing a perfect redox peak for this measurement that I've shown. To redox the state of this molecule, red for the oxidized state and blue for the reduced state of the molecular structure. So here it shows the conductance measurements of AQ15. We can see in the blue region, blue potential region, that we have the reduced form of the molecule, with again moving from positive potential to more negative values. This gradual decrease in the conductance is observed because of Fermi level shifting. So we can see a very sharp decrease in the conductance, switching of the conductance in more than one orders of magnitude. And with again moving to more negative potential value, we can see this gradual decrease in the conductance. In the case of AQ14, we have seen more or less the same phenomenon that I explained about AQ15, except in the reduced form of the molecule, first we increase the conductance. So a sharp decrease in conductance, but not less than one order of magnitude, not more than one. So it was smaller compared to AQ15, and then again with moving from negative to more positive values in the potential region that we have the oxidized form, we can see this gradual decrease in the conductance value. So from the calculation point of view, these ones are the transmission curves calculated for these measurements. So in both molecules, AQ15 and AQ14, we can see that the reduced form of the molecule has higher conductance compared to the oxidized form of the molecule. So in the case of AQ15, we can see this decrease in conductance. This switching factor is higher than AQ14. It's because what I said, different electron pathways through the molecule. In the case of AQ15, the electron pathway is going through this anthraquinone. So with oxidizing this anthraquinone moiety of the molecule, we have cross-conjugation quantum interference effect. And that's why we can see big switching effect for this molecule, but not a big one for this molecule, for AQ14. So in the case of AQ14, with oxidizing, we have an electron withdrawing group attached to the backbone of the molecule, decreasing the electron density here, and we can see a small switching effect for AQ14. Later, we have tried to replot these transmission curves versus a real reference electrode using this scale that you can see here is published in 1986, and with this factor or with this number versus saturated hydrogen electrodes. When we replot the data, here it shows the experimental result, and here we can see the theoretical calculation replotted versus the saturated column electrode. So the experimental result, the big dots here, and the theoretical calculation are showing a very perfect agreement based on this data replotted here in the both case of AQ15 and AQ14. So now we have learned how to tune the conductance, how to switch the conductance, apply these two different ideas in one molecular system. Now it's the time to improve the quality of our switch and monitor the phenomena that we know in single molecular conductance measurements. So now we can see in this molecule, in the anthraquinone-based molecule with the proper ranking group, of course, we can see a region in the transmission curves that we have the anti-resonance here, quantum interference effect, but when we have the linear conjugation, this quantum interference is not observed. So what we want to do, we want to see how this data works for a molecular system that we can see here. We have synthesized this molecular anthraquinone-based molecule with higher anchoring group. First, we measure the conductance of this molecule in the potential regions that we have the oxidized form. So we have this quantum interference effect, and we didn't see any plateau for a single time distance thesis. and one-dimensional histogram, which shows that the conductance of this molecule is falling below the noise level of our instrument. But as soon as that we change the potential to the values that we have the reduced form of this molecule with the linear conjugation, the clear plateau is observed at around 10 to minus 4.2 G nodes. So from this data now we learn that we have a switching factor for several orders of magnitude. But if we want to know what exactly this switching factor, this on-off ratio is, we need to somehow monitor the low conductance state of this molecule. For this purpose, we have used our new STM break junction setup with higher mechanical stability and logarithmic preamplifier that we have the noise level at below 10 to minus 8 G naught. So we were able to monitor the low conductance state of this molecule at around 10 to minus 7.3 G naught. So this data shows a switching factor more than 3 orders of magnitude for this molecular system, which is highest one reported up to now. Later we tried to check the switching effect of this molecular system from low oxidized to reduced form, and after 5 different cycles, still we could recover the peak for the oxidized form of the molecule, showing the high reversibility of this molecular switch. So we tried also to monitor the conductance in the potential regions that the molecule is redox inactive. We started from the reduced state of the molecule. We can see again this phenomenon shifting the Fermi level of the electron. A very sharp decrease in conductance for the switching effect, more than 3 orders of magnitude. And with further sweeping the sample potential to more positive values, we can see for the first time experimentally this quantum interference effect that we have seen in the transmission curves calculated for these measurements. First is decreasing and then increasing this region. So now brings us to the conclusion and summary of our data. We have learned from the redox inactive molecular system that we can shift the Fermi levels of the electrode up or down with changing the sample potential or electrochemical gating potential and finely tune the conductance. We can switch the molecular conductance in the case of molecular system that they are redox active between the different redox state of the molecule. We can combine different ideas in one molecular system. We have shown in the case of anthraquinone-based molecule with gradient anchoring group, and we can also increase the quality of our data with using the proper anchoring group and proper backbone of the molecule for having very high on-off ratio molecular system. But to see the outlooks for molecular electronics, I have talked already that the idea is using to apply this molecular system in the electronic circuits, but this idea is still far away from the reality. One of the accessible application of these measurements would be for chemical sensing. For this purpose, we have established a collaborator with Professor Thomas in Johns Hopkins University. They have synthesized these 3 different molecular systems for us based on tyrosine and boron here. These molecules can attach specifically to fluoride ion, but not other hydrogen or anions. So we can see in the case of this molecule, we have the electron pathway going through here. So if you attach the fluoride to this system, we don't see any big change in conductance. But for the case of this molecule, since the electron pathway is going through the boron, and block and have quantum interference and change in conductance in several orders of magnitude that can be used ideally for this sensor or chemical sensing application. So here it shows some publications of mine during the PhD translated ones. And again, I would like to thank the people in the Electrochemical Nano-Science Group. First of all, Professor Thomas Wandlowski, he has offered me this position as his PhD student. I had the opportunity to work with him for more than 1 year, and I have learned a lot from him. But that sad story happened. But it brought us with some other opportunities that I have worked with Dr. Peter Brockman, Professor Hans Siegenthaler, Benjamin Horn, and they have helped me a lot to be here now defending my PhD. So all the people in the Electrochemical Nano-Science Group, Dr. Garcia, he was tutoring me during the first year of PhD. Of course, the founding agencies, Swiss National Science Foundation, Acmon Project, and the University of Bern. And thank you, Silvio, to be chairman of this one, and Dr. Kalame to accept to be the examiner of this PhD defense. Thank you very much also for your attention. Don't forget the apro at around 5:30 in the club room in the 5th floor, and please ask questions.
Thank you for the presentation. And we go straight to the discussion part. We have plenty of time. Michelle, you may start.
Thank you, Silvio. First of all, thank you, Masoud, for the nice presentation. It was a pleasure to read your PhD. So let me try to dive a bit into it, and I would like to start maybe with a simple point. Right? You mentioned that there are different techniques to measure these molecules, and you mentioned mechanically controllable break junctions. You used mostly the STM break junction, and you mentioned that for the gating experiment you were mostly using the STM, but this is not possible for the mechanically controllable break junction. So to start with slowly, are there differences between the two approaches, or is this exactly the same thing? And then version B of the question, or part B of the question is why can't we do electrochemical gating in mechanically controllable break junction?
So this is from the technical point of view that we are dealing with. So I said here, I've said here, this shows the STM break junctions that have potential control. I've said here that we coat the tip in the parts which are in touch with the solution. So why do we coat this tip at this, for these parts? It's because we want to avoid Faraday or non-Faraday current on the tip. So we coat all the parts except very apex of the tip, which the tip feels the tunneling current. So in the case of mechanically controlled break junction, coating one of them, or we notch the wire usually, so coating is not practically possible for us.
Or not? You can do lithography and you deposit some nice polymer resin, use the E-beam to open nice gap, no problem. So can be insulated in principle. So that would be the limitation in principle.
I think they have tried. I didn't personally try it. Yeah. I think they have tried, but the leakage current should fall below 1 or 2 picoamperes for this measurement. Mm-hmm. The methods that we have for coating is not so nice for coating like wire for the scanner for the mechanical control break junction.
Okay. Yeah. So that would be the main reason. Yeah.
Yes. For the AFM also we have the same problem. Coating cantilever is not that easy, so usually we have very high leakage current. Mm-hmm. So theoretically it's possible to apply this electrochemical gating control potential, but technically it's difficult. So it's easier to use STM break junction for this purpose.
Mm-hmm. Okay. Yeah. And then are there some differences between the two approaches, you think? Or not? I mean, you guys you're one of the very few groups having both approaches in the same lab, right?
Yes.
So is it the same? It's like if you take the same molecule, you can remove the gating, and you measure it in both systems, you get the same value, some differences sometimes, or? Yeah.
Yes. So technical, like systematically, there should not be a difference. They are just working based on this metal-metal junction, withdrawing, making a gap, this break junctions. But in our setup, usually since we in the Scanning Probe Microscopy, so tip moves directly toward the substrate. But in the mechanically controlled break junction, we have this plate which is flexible, so we can control the distance and we can have more mechanical stability. In the case of mechanically controlled break junction with lower rate of movement. So, but systematically based on mechanism, they are both the same.
Yeah, I mean, we all expect that they are the same, but it doesn't seem that everybody thinks the same, right? If you look in the literature, the differences are sometimes pronounced.
Yes.
So, why?
It's because of different rates, for example, that we are measuring. Okay, this, I can show these slides. Here. So we have studied these molecules, series of molecules with two different systems. So we have seen just a small difference, in all the molecules it was the same when we measured with STM break junction and MC-BJ. But in just one molecular system we had small differences we didn't really find a good explanation for this one, but maybe it's coming to the different approaching of withdrawing rate that we are using. So in the case of MC-BJ, if it's very stable, mechanically it's more stable, and with lower rate we have higher stability of the molecule in the junction, so it can form like different configuration compared to STM-BJ junction. So if it's faster, the thermal effect is affecting the molecular junction less than MC-BJ, which is slower. So these things can bring some differences between these two different techniques.
Okay. I agree, timescales are not the same for both systems. But now if we just take one more minute about this one, like, so what is a typical timescale for the reorganization of the molecules within the junctions? What would be your guess? Is it like how much, you know? I
would say in the range of a few milliseconds.
For one molecule?
Could be. I have a movie, maybe I can show it here. I can find it. So if you have like different